Okay, everybody, so welcome back. Let me go ahead and start where we left off yesterday, which is we had this discussion of a process or thing, situation that we were trying to model, and through some means we have constructed or found a model matrix for this process. And the way that we're going to model it is as such, basically. So we begin with some initial data vector. Again, this and the model matrix may have been constructed from empirical data collected from whatever, in whatever way, or wherever we've gotten this thing. We are attempting to model this situation in the following way, which is we have initial data vector, we have model matrix, and iterating to the next time step, so going from 0th time step, the initial data, to the next time step in this process involves multiplying once by this matrix on the left. So taking initial vector, multiplying by the matrix, this gets us to first time step, second time step, and so on, iteratively multiplying by this matrix. And so to get to, for instance, the kth time step, so to completely describe any time step here, all I need to know, rather than trying to keep track of all of these intermediate vectors, I don't need to do that actually. All I need to do is know powers of this matrix A and multiply that by this initial vector, and that will get me to the kth time step. So this is really nice because I don't even need these intermediate steps, unless I'm specifically interested in some specific time step. I can get to a generic time step knowing just powers of A. Well, the only problem with this, the only thing that makes this not like perfectly nice, is that powers of A are nasty. So in this whole process, we're assuming that A is a square matrix, right? So it's an n by n matrix. So all of these powers, of course, are also n by n. They're the same size. But the way that this goes, right? If you were to just write this out, even for a 2 by 2 or even for a 3 by 3, and I should point out that for a variety of applications in this course, when we are actually doing some of these applications, not just in this case, or we're going to start least squares later. Whenever we're doing the by hand examples, the matrices are going to be pretty small, but of course, when you are actually doing this, when you're applying this to some thing that you're encountering in the wild or something you're trying to model, typically these matrices are going to be huge. Okay, they're going to be very, very big. And so, obviously we're not going to do that by hand. It would be far too tedious, but the point being is that even in the case when you have like a 3 by 3 and you are trying to compute powers of the 3 by 3, you can just try it, right? Like if I write this out, I'm just going to shorthand the notation here because I'm going to here's my 3 by 3. I think I know my alphabet. Did I skip any letters? Maybe not. Right. This is me multiplying a 3 by 3 by itself, right? We'll say this is A times A here, right? And if you just start even from the very first entry, you can see that what's the first entry in this going to be? The top left, I'm not going to write the whole thing out, obviously, but this entry right here is going to be A squared plus B times D plus C times G. That's going to be this entry. And you can see from the very first entry, there's not some like nice pattern or anything you can notice other than you're just multiplying two matrices, right? So any hope that you might have had that like you're going to just write this somehow as like squares of entries, it's clearly not going to happen, right? So, and it just gets worse from there, right? This is just squaring the matrix, right? Cubing the matrix or raising it to higher powers makes it even nastier. So what do you do, right? Like this is nice. Like theoretically, this is a nice setup that in order to get to a generic time step, all we need is to know powers of the matrix, and we start with the initial vector, so we will know that, right? So really, this whole process is governed by iterative multiplication, just powers of this matrix. Okay, so but it seems that computing powers of matrices is not super nice. So what do we do? Well, first we might hope that we are dealing with a matrix that is nice to compute these powers. And so maybe here's a question to start with. What matrices are nice to compute some A to the K for? Okay, it's not the greatest sentence construction. So what matrices are nice to compute this generic matrix power A to the K for? And the answer is, or one potential answer, of course, you might say zero matrices, right? If the matrix is all zeros, raising it to whatever powers, it's just going to be nothing but zeros. So raising zero matrix to a bunch of powers is a zero matrix. That's about as nice as it gets in terms of computation. That is a subcase of the main thing we're going to talk about, though, which is diagonal matrices. So diagonal matrices are, of course, very, very nice in this way. And so what is a diagonal matrix? Just to remind you, so a diagonal matrix looks like this. So a diagonal matrix looks like this. Anything can be on the diagonal. So in a square matrix, so first of all, a diagonal matrix, maybe I'll use the letter D here. A diagonal matrix has to be square, okay? The only matrices that have a diagonal are square matrices. Rectangular matrices do not have a diagonal. What is a diagonal? A diagonal is in the Aij, or in this case Dij, matrix notation. The diagonal, or the main diagonal, sometimes it's called, is the thing that consists of the d sub ii terms, right? So it's the terms in the first row, first column, second row, second column, third row, third column. It's these asterisks, these stars that I'm writing. It's these things, okay? So a diagonal matrix has whatever here, okay? These can be anything. That's why I've written them as stars here. They could be 0. They could not be 0. It doesn't matter what those are, but the main thing is that everything else is 0. So nothing but zeros above the main diagonal, nothing but zeros below the main diagonal. So zeros everywhere except on this main diagonal, which could still be zeros, but might not be. So maybe all of these stars are non-zero, but some of them could be 0. In fact, all of them could be 0. So note, the 0 matrix is a diagonal matrix. So that includes this case that all those diagonal entries are in fact 0. Okay. Now, I could use this opportunity very quickly to. I think I'm just going to say it in words. I'm not even going to write it out. There's other types of matrices we could talk about here: upper triangular and lower triangular. An upper triangular matrix is one where everything below the main diagonal is 0, but maybe all these terms are non-zero. It's called upper triangular because you can draw a triangle in the upper half here. Lower triangular is the same thing except in the lower half, so it's basically only this top right thing would be 0. Everything else could be non-zero. So a diagonal matrix is both upper and lower triangular. Maybe I'll write that out. So a diagonal matrix is both upper and lower triangular. The main reason you like triangular matrices in the main context in which they came up in linear algebra before is that it was very easy to compute the determinant of triangular matrices. Okay, so again, if you need a refresher on any of that stuff, you can look at the review section, and I'm going to bring up these things as we need it going forward. That's how this course is going to work. We're going to dip into material that you have seen before as we need it basically. And if you don't remember seeing it or haven't seen it or whatever, then you can pick it up in review in the review sections. So anyway, so I claim that the diagonal matrices are nice to compute this a to the k for. Let's just see how that works. So let's have a diagonal matrix D, and I'm going to write it like this. I am going to write it suggestively like this. Let's say that this is my diagonal matrix. So those are its diagonal entries, lambda 1, lambda 2, and everything else is 0. 0 everywhere, 0. All this is 0. Okay. What is d to the k? You can very quickly work this out, that in fact, this is the thing that you would love for it to be. You simply exponentiate these things. The diagonal entries get raised to the kth power. Everything else remains 0. So not only is it easy to compute, it actually remains a diagonal matrix. Okay, so powers of a diagonal matrix are still a diagonal matrix. Okay. Now, the problem, of course, is that going back to this original statement, okay, that's nice that diagonal matrices are easy to raise to powers, but the model matrix that I started with, this came to me as a means of modeling some process, right? So this is not necessarily a thing I have much of a choice in, really, right? This matrix comes from being the best matrix I know of that models the situation that I'm in, right? So it's not like I can just choose for this thing to be diagonal. It very likely is not going to be diagonal. A diagonal matrix is extremely special, right? Like you pick a random matrix out of a hat, the chance that it's diagonal is like 0. So how do I get here? How does this help me? Well, this is where the notion of diagonalizability comes in. Now, depending on the instructor you had in 240 or wherever you've seen this before, there could be a little bit of confusion when it comes to this terminology. Every time I say diagonalizable in this course, I'm going to mean diagonalizable over the reals is what we'll say. So what do I need here? So we need the notion of diagonalizability. So two things. I need the notion of what is called similarity. Matrices A and B are similar if there exists. And in the future, I'm probably going to shorthand this with this symbol just to make life easier when writing this. If there exists an invertible, we'll say these are n by n matrices. If there exists an invertible matrix, we'll say P such that A is equal to P, B, P inverse. Depending on your background, you might recognize this as being an example of what is called conjugate elements, or lying in the same conjugacy class. But that is in the world of matrices, we call this similarity. These are called similar matrices. And there's a whole host of things that are true about similar matrices. I'm not going to get into all of them, but for instance, the big one, the main reason that this is, this is introduced when it is typically in linear algebra, is that you might remember that similar matrices have the same eigenvalues. Okay, so similar matrices have the same eigenvalues. So we are going to write following definition: a matrix A, which is an n by n matrix, is diagonalizable if it is similar to a diagonal matrix D. Okay. Now, you may also recognize this similarity business. So in this case, A is, there exists an invertible P such that A is equal to P, D, P inverse. Now, you may also remember from linear algebra or wherever else you've seen this, that another way of thinking about this relationship between A and B is that this matrix P could be thought of as a change of basis matrix, essentially. It is a matrix that allows you to change basis, and in the new basis, the matrix A is B, or vice versa. Depending on, that's another thing that I didn't mention. Like this similarity, there's no directionality to this. Like it doesn't matter if you say A and B are similar or B and A are similar, because if A and B are similar in this sense, then you could put B on the other side by just using P inverse instead of P. So so all of this still very much works in either direction. So for that way, changing basis, whether you're changing from matrix A to B in the new basis, it doesn't really matter. You can go back and forth here. You could think of P as a change of basis matrix. Okay, and so you have changed the basis. You had a basis that you're considering the matrix A. In the new basis, A looks like B. It is B with respect to the new basis. Okay, so and that's important for what I'm about to say. But this is so a matrix A is diagonalizable if it's similar to a diagonal matrix. Okay, before I go any further, I'm going to immediately say why this is nice. So I'm going to say if A is diagonalizable, right? I had this statement that, or I still have it on this page. For a diagonal matrix, raising it to powers is very, very nice. If A is diagonalizable, what do I get here? Let's say I want to compute A to the K. Okay. In fact, let's start simpler to see how this works. Let's just do A squared. But A is PDP inverse. But what is this? PDP inverse squared is, if I just write it out all the way, this is PDP inverse times PDP inverse. Now remember, matrix multiplication is associative, so I can change the order of the parentheses, but I cannot change the order of how these things are multiplied. And that's another thing, right, to remind yourself here. You might say, wait, this doesn't say A is equal to B. No, I can't change the order of the matrix operation, right? Matrix multiplication is typically not commutative, so I cannot change the order of the letters that show up in this string. I can't change the order of those, but I can change the order in which I multiply them, right? So I have associativity, but I don't have commutativity. So here, for instance, by generalized associative property, I don't even need parentheses. There's no ambiguity here, just writing this as a string. This is what I have. So I can do this multiplication first, for instance. P inverse P, notice I did not change the order here, right? P inverse P is the identity. So this is P D times the identity times D times P inverse, which is P times D times the identity is just D. D times D is D squared. So A squared is equal to PD squared P inverse. What this means is, by a similar argument, A to the K is P D to the K times P inverse. Okay. Okay. How does this help me? Well, this is saying that if A is diagonalizable, then the powers of A are also diagonalizable, and another way of saying that is they are similar to a diagonal matrix D, but specifically they're similar to D raised to the kth power, which is an easy thing to compute, right? Again, how does this help us? The idea if A is diagonalizable, we can change basis to a basis for which A is a diagonal matrix and compute A to the K in this way. Here are some facts about this that you may recall or may not. There's a reason that I wrote the diagonal matrix D using lambda as the diagonal elements, because if A is diagonalizable, then those diagonal elements are the eigenvalues of A. So facts 1, D is determined by the eigenvalues of A. Okay. So this is determined by the eigenvalues of A. 2, A is diagonalizable if and only if A has n linearly independent eigenvectors. This is called the diagonalization theorem. Okay, now, in 240, considerable effort goes into saying whether or not a matrix is diagonalizable. You have to find all of its eigenvalues and eigenvectors, and then the dimension count of each of the eigenspaces has to be right. What are the eigenspaces? The eigenspaces are these null spaces. I haven't talked about null spaces yet. Those are included in the review material, but we'll talk about them when we need them. This had to do with counting the dimensions of the eigenspaces, which are these null spaces. Those dimensions needed to equal the algebraic multiplicity of the eigenvalues. So each of the eigenvalues is a root of the characteristic polynomial. It's a root of some multiplicity. Multiplicity 1 is a simple root. Higher multiplicities would be a double root, triple root, whatever, if you've fully factored your characteristic polynomial. One thing to note is using the terminology we're describing. If A has a single complex eigenvalue, it's not diagonalizable in this sense, since we're talking about diagonalizability over the reals. Situation's a little bit more complicated. We need to get into some other things if we want to talk about slightly more expansive notion of diagonalizability, but I'm not going to get into the weeds there. So the point being, the main point, going back to this, and the whole reason that I mentioned this, is that this whole situation, this entire situation, is governed by eigenvalues of A. So that is the important bit, and that is true not even just in a purely linear algebra course. If you are dealing with even, say, differential equations, so systems of first-order differential equations, linear planar systems for differential equations, the long-term behavior or the behavior of the system you're dealing with in general is essentially entirely determined by the eigenvalues of the matrix corresponding to that system. So in the context of linear algebra, we have this process being modeled by this matrix A, and understanding like asymptotic behavior or long-term behavior or just behavior of the system itself is entirely determined by the eigenvalues. So much so that, in fact, even if you did not know what the matrix was, your original matrix, you're not even sure exactly what it was. Knowing just the eigenvalues alone, you would be able to say a lot. Basically, you'd pretty much be able to say everything that you want to say about this. And so this is the main way of understanding why eigenvalues are important in this way, and we will see this later in the course. So all of this kind of fits, nicely here at the beginning, just as kind of reference material and slightly more expanded discussion of these things, but there's a nice review chapter in Justin's notes that you can have a look at if any of this stuff is confusing. The other good thing is if any of these particular topics are confusing, so if I mention a linear algebra notion, you don't quite remember it, and it's not really covered in the review material, you can look it up. Even like even a Wikipedia entry on these things is like very expansive, because these are very, very standard things, and you're not going to get confused by notation or anything, because all of this is so standard. Okay, so I think that's more or less what I wanted to talk about. There's obviously, we get into the weeds with a lot of these topics, because there's there's a lot of the conceptual, for instance, I could even talking about similar matrices, there's all kinds of questions I could ask you, true false questions about what is true, knowing that two matrices are similar, how that relates to matrices being row equivalent, all kinds of things like this could be asked, but we're not gonna focus too much on that. Those questions will be naturally answered as we go through the material. So what I wanted to start on instead is, you'll notice that this isn't quite in order in terms of the way that the chapters are listed, but that's the point of why there is no numbering of the chapters in the notes. We can cover this in any order, kind of. Like I said, some of them go together. So we are going to talk about least squares. We'll see what that term means. We're going to talk about least squares, and this is going to lead to curve fitting next. Which will be the next chapter we do after this, because they do go together. But they need not necessarily go together. This is just it's just very very nice. Like we could technically take a break and cover something else before going to curve fitting, but it makes the most sense to do curve fitting immediately next. But what is least squares? So maybe let's start with like the most basic. This is why this is kind of appealing to start with. Start with the most basic expression in linear algebra, the thing that is fundamental. This matrix equation, AX equals B, right? So recall, there are three cases, right? So three cases. We could have zero solutions. We could have one solution that's unique. We could have infinitely many solutions. Those are the three cases. Now, here's kind of what we'll say here. Let's say that we would like to find a solution to this equation. So we're not happy if we are in this case. Now, this is the name of the course is Applications Linear Algebra. So we're doing some kind of application problem, which means that we have a slightly different motivation, right? Like in the purely theoretical sense, if we have an equation before us, AX equals B, and it doesn't have a solution, well, then it doesn't have a solution. And we might ask a question about like, well, what's the closest possible solution to this thing? But we're naturally motivated to do that if this is an application problem, because maybe, I am seeking a solution to this thing for some reason. I would really like this thing to have a solution, but it doesn't. So that's not exactly the end of the road. We know what it means to be in this case. If it has one solution, A being invertible would tell me that this has one solution. Okay, so then let's say if I have infinitely many solutions, I'm happy because I got plenty of solutions to pick from. So let's say that I'm in the case that I have 0 solutions. Okay, um, but the question naturally is, if no solution exists, can I find a closest to being a solution vector? Okay. Now notice I didn't say anything about A being, I didn't say anything about A being square here. But the question is, I'm looking for a solution that is closest, or not a solution. It is definitely not a solution since this thing has no solution. So since it has no solution, I'm not looking for a solution to this because that would be silly. But I'm looking for a vector that is closest to being a solution. Okay, so the question is, I'm looking, i.e., I seek some x hat, we'll call it, right, such that, well, let's think about this. I want it to be the closest to being a solution. What does that mean? Well, what is the thing that I'm trying to minimize? Well, if x is a solution to this, then ax minus b is a 0 vector, right? Because ax is equal to b. But if x is not a solution, this is not the 0 vector. And if no solution exists, then any x is not a solution. And so for any x, this is not the 0 vector. Well, from what we know about the length of vectors, right, if something is not the 0 vector, then the length of it is not 0, right? Since one of the properties of inner products and properties of the dot product is that the length of any vector that is not the 0 vector is positive. Okay? This is known as positive definiteness. So, the length of this is positive. So the length of this vector is positive. And so what I want is to minimize this positive quantity. I want to minimize this length. And now we see why this is called least squares, right? Do you see it? Well, the length of a vector involves a sum of squares, right? And the length of a vector is the square root of a sum of squares. And we are minimizing, if you minimize the square root of a thing, you're minimizing the thing under the square root, right? Since square root's an increasing function. So we are minimizing the sum of squares. Hence, we're seeking the least squares, right? We are minimizing the sum of squares term. What do I mean by finding an x hat that is closest to being a solution? I mean that this quantity is always less than or equal to this quantity for any vector x. Okay, in the vector space in question. So this is what I seek. I seek an x hat that minimizes this length so that ax minus b, whatever it is always less than or equal to this expression, the length of this thing. You might notice here that the notion of closest then is not necessarily going to be strict. So what that means is that, note, this x hat may not be unique. I did not claim that it was unique from this description. So just throwing that out there, in terms of what I've written so far, this need not be unique. Okay. All right. So how do I do this? It might not be apparent at first. And this is where knowing the conceptual picture actually makes going after the solution a lot simpler in a lot of ways. So that's what we are going to do. We are going to actually look at the picture here, and so let's see here. And so let us first write out definition of the column space. So the column space of a matrix A, this may be a rectangular matrix, is it is the span of the columns of A. So I'll write it like this, just to stress this. If A can be written as, just like I did yesterday, I told you that there's some instances where it is more convenient to write a matrix as a list of column vectors in this fashion. So this is the span of the columns. I defined span in yesterday's review lecture. This is the set of all linear combinations of these things. Maybe writing that out in words is also good to stress this. The set of all linear combinations of the columns of A. Since it is a span, we immediately get the following fact. Just like I said yesterday, the span of a list of vectors is automatically a subspace of the vector space where those vectors live. The columns of A, where do they live? The columns of A, there are n of them, but they have m entries, so they live in Rm. And so the column space of A is a subspace of Rm. Okay, it's automatically a subspace of Rm. Now, it may be all of Rm. It could be. But it might not be. Okay, so it is not guaranteed to be. Okay. So, how does this help us? Before I go into that, I'm going to revisit what I said yesterday about the equation ax equals b. So recall, and again, this is from yesterday's lecture, that the equation ax equals b can also be phrased as, so seeking a solution here can also be phrased as is b in the column space of A. Or, writing that out a little bit more, is B a linear combination of the columns of A? I asked this question yesterday in our review session. So is B a linear combination of columns of A? Finding a solution here is the same as answering this question. If there is no solution, then the answer to this is no. Okay. So a quick example here, and I'm just going to use the same example from the notes, which is say that we have the equation, I'm going to read row-wise, so 1, 2, 0, 3, minus 1, 0, times the vector x, which needs to be a vector with two components here, is equal to the vector b, which is 4, 5, 6. Solving this amounts to doing what? So if I multiply this out, right, and then refactor, this is what I'm doing. So this, I'm going to do the matrix multiplication here so that I get a vector of 3 components here. So this would be 1 times x1 plus 2 times x2 in the first slot. In the next slot, this would be 0 times x1 plus 3 times x2. You might say, why are you writing these out? It's just to make the next step more obvious. Minus 1 times x1 plus 0 times x2. And that is equal to 4, 5, 6. Of course, you can see now that I can recast this as that vector equation just like I did yesterday. I did this yesterday in the review lecture. So I can write this as the column 1, 0, minus 1 times x1 plus the column 2, 3, 0 times the weight x2, and that is equal to 4, 5, 6. And so we've just literally turned this into exactly this thing. We're asking the question of, is the vector 4, 5, 6 a linear combination of the vectors 1, 0, minus 1 and 2, 3, 0? You see directly how this question is AX equals B, because here's the two columns of A. Finding an x1 and x2 that satisfies this, right? So finding an x1 and x2 that makes this work would exactly be finding the weights in this linear combination. Okay, maybe those weights exist, maybe they don't, but the point is that either way you are answering this question. Okay, and so, well, how does this help us understand what's going on in the picture? The idea is that this column space of A is a subspace of Rm. All right, so we can think of Rm being like the ambient space. Again, like I said, maybe the column space is all of Rm. You can think of this typically as like a plane. Okay, so here's the plane sitting inside some ambient space. Maybe the whole space is the plane, okay, but the point is like here is some plane. If you like to, here's like the origin of the plane. Here's the 0 vector. If you like to think about it like that, and this plane is expanding, it's infinite in all directions. So this is my column space sitting inside Rm. Maybe it's all of Rm, maybe it's not, but this is what it looks like. Now, what if AX equals B has no solution? Well, if AX equals B has no solution, then, I'm off the page. Hold on. There we go. All right. If AX equals B has no solution, then what I know is that B is not in the column space of A. Okay. But B is in Rm. So note that in this situation, this column space of A is not all of Rm, right? Since if it was, it would contain B, but it doesn't. So it is not all of Rm. So it is sitting inside Rm. So you can think of the page as being Rm space and this plane being some plane in Rm passing through the origin. So B is in Rm, but it's not in the column space, which means that the vector B, maybe it's like here, right? So here's B. Okay. B does not lie on this plane. Okay, it is off this plane. It is, again, I'm drawing a thing that is, I'm drawing a plane on a 2D page. So, you might say, oh, it's just off the edge in this direction. No, it's above it. We'll see. Here, I'll add some perspective here in a second. And the question is, how do I find not a B, like I know what B is. I'm given that thing. That's not in my column space. But how do I find something in the column space that is as close to B as possible? Well, what I would do is I would somehow project this B onto my column space in a way that this is as close as possible. And it turns out that the way to do that is to project orthogonally, so that this is a right angle. This is perpendicular. Okay. Well, you might automatically, I've already used the words basically that give it away. And so I'm looking for this B hat that is something that's in the column space that is as close to this B that's outside of the column space as possible. And so the question is, what is this thing? And the answer, it is the orthogonal projection of B onto the subspace call A. Now, the orthogonal projection is a thing that we did in Math 240 or linear algebra, or even in Calc 3. This is done onto a linear subspace, not onto a generic subspace. But this involves, it's an expression involving dot products. Okay, it's also the essential tool in the Gram-Schmidt process, essentially. So Gram-Schmidt process for constructing an orthogonal basis that we talked about yesterday, that uses orthogonal projection. So writing this out in symbols, this B hat is the projection onto the column space of A of this vector B. Okay. All right. And so, now what do I say? Well, so then my idea is to solve not the original equation, but to solve AX equals B hat, or AX equals, writing it out here, the projection onto the column space of A, the vector B instead. Okay. Now, here's the thing. This works just fine, but the issue is that finding, so note the issue here is that finding this projection onto the column space of B is actually kind of annoying. It's straightforward, but it is kind of annoying. But there's another way to find it. There is a roundabout way of finding it, finding the same solution we seek, that is slicker, that is nicer. Okay, typically substantially nicer. So how does this work? The idea here is as follows. Here's our ideas and things that we notice. Okay. So maybe we'll start out. So one, find solution. We'll call it x hat, such that ax hat is equal to this projection onto the column space of A of the vector B, or ax hat equals b hat is a slicker way of writing it. And two, we need to ensure that this thing actually, this x hat, hopefully satisfies this condition that it actually minimizes the squares in question, right? We want to make sure that this actually minimizes this expression, that it satisfies this. That's the whole purpose, right? So this hopefully satisfies that the length of ax hat minus b is less than or equal to the length of ax minus b for all x. And it does. I'll go ahead and spoil it for you that it actually does. So let's start with 1. So let's start with 1 first. How to do this. So I'm looking at the equation, right? ax equals b hat, or ax equals the projection onto the column space of A of B. Okay. Now, if I draw this picture here, so I'm going to draw my column space. Here's my column space of A as a plane drawn in this way. Here's, we'll say, my 0 vector, which always is in any subspace, but it's definitely in my column space. Okay. The x hat that I find, right, what the solution to this, if we're calling this x hat, so x hat is my solution. It has to be in the column space, x hat doesn't have to be in the column space, but ax hat has to be in the column space since it is equal to this projection, right? So note, if x hat's a solution, then ax hat equals b hat, or this projection, which is definitely in the column space. So ax hat is here. This is b hat. This is my thing that I am projecting. So if I draw a line between those things, this point, this b hat, by definition, is orthogonally projected B onto the column space. Right? Now, I know that, like I said, I haven't technically written out what the orthogonal projection is, but here we're just doing this intuitively. You have seen orthogonal projection in some point or in some form before. You can have a look at the review if you want to see actually how to orthogonally project, but we don't actually need it here. We just need the fact that this is orthogonal. Okay? And so, what is the point here? What do we notice? So note that, for instance, this vector here. So if here is my vector b, and here is my vector b hat, what is this vector? All right, if I'm thinking about that as a vector, what is that? Well, by my part of my parallelogram rule for how vector addition works here, this is ax hat minus b. That's what that vector is. The fact that this b hat is the orthogonally projected b means that this ax hat minus b has to be perpendicular or orthogonal to all of the column space, right? So note ax hat minus b is orthogonal or perpendicular to the column space. Now, what does it mean to be orthogonal to an entire subspace? It means that you are orthogonal to any vector in that subspace. It means you pick any vector in that subspace, and when you dot it with that thing, you get 0. Okay, so so that is what it means. Okay, and so what does this tell me? Note, for any x, ax is by definition in the column space of A. So ax hat minus b is perpendicular to the column space, which means it's perpendicular to any vector in the column space. Ax is in the column space. So ax dotted with ax hat minus b is equal to the 0 vector. And that is true for all x. But if that's the case, I'm going to rewrite that on the next page. All of these remaining statements are going to be true for all x, so I'm not going to rewrite that. Dotting, of course, I know what the dot product is, but you can write the dot product as matrix multiplication, right? So a way of writing the dot product as matrix multiplication is transposing the thing you're dotting and then multiplying it as matrix multiplication. And so a way of writing this instead is to write this as ax transpose times ax hat minus b is equal to 0. And this is true for all x. So here's a quick aside. What is the transpose? So A transpose is the matrix. I'll write out the word. A transpose is the matrix formed from A by replacing, or maybe I should just say, I think it's easier if I just say informally what it is. So it's swapping the roles of rows and columns. Now, what do I mean by that? i.e., the ith row of A transpose is the ith column of A, and vice versa. Okay. So, you know, a very easy way of writing this, if you're writing it in terms of entries aij, is it's swapping aij with aji. So that's what the transpose does. So one property of the transpose is that. So here's a fact about the transpose. So it reverses the order of matrix products. Of course, another property of the transpose is that the transpose of the transpose is the matrix itself. Transpose doesn't affect determinants. That's another thing. Maybe I'll just go ahead and write that because we're talking about it, so might as well. So swapping the role of rows and columns, you should remember from the definition of the determinant, in cofactor expansion, the way that it works, since you can go across any row or down any column, this has to be true. that swapping the rows and columns does nothing, so to the determinant. So there we go. Anyway, so in particular, this means that from this first fact, transpose applied to this reverses the order of this thing. So this is X transpose times A transpose now times AX hat minus B is equal to the 0 vector. Okay. Now, what does this do here? Well, how do I? So let's see here. So X transpose, this X is a column vector. Now this is written as a row here. What is actually important is maybe I should, sorry, this is a dot product, so this is a little bit confusing that I'm writing this as a vector. This should just be 0. Okay, I don't know if anybody mentioned that, but if not, I'll clear that up preemptively so that it's not confusing when you're going back through this. So yeah, this is a dot product, so obviously the right-hand side has to be 0 here. Here, if this is going to be 0, then multiplying by this X transpose at the end, if this is going to be 0 for all X, then the thing you are multiplying by needs to be the 0 vector. So for instance, this means A transpose times AX hat minus B is equal to the 0 vector. But then distributing this is A transpose A times X hat minus A transpose B is equal to the 0 vector, which tells me that A transpose A X hat is equal to A transpose B. Well, what am I doing here? Notice that I could have really gone in any direction here, and so all of these could be turned into if and only if statements. And so what did I start with? I started with the assumption that what we were dealing with, this AX hat minus B, because of the construction, had to be orthogonal to this B hat, which is AX hat. And in that way, I've obtained this equation, or this system of equations, you want to think about it this way, so that, note, a solution to this finds the X hat I am interested in. So we simply solve this equation instead. Now, you might immediately ask a question. Okay, we started with an equation. It didn't have a solution. Now you're telling me to find this potential candidate as a closest thing to a solution here. I solve another equation. Well, what if that equation doesn't have a solution? But you might notice that the way that we have constructed this has to have a solution. Okay? It might have more than one, right? But it has to have a solution because you are solving this thing that we set out to solve, this projection equation, which by construction has a solution because we've actually moved the right-hand side vector to the column space, so it has to have a solution. So this absolutely has a solution, but it might have more than one. It might have infinitely many. which is not really a problem for us, right? That just means we're not gonna have a unique closest solution. We're going to have infinitely many. So there's going to be a bunch that are as close to being a solution as each other. So that's just a feature. In fact, note this will have a unique solution if and only if A transpose A is invertible. But this happens exactly when A has linearly independent columns, i.e., when A has linearly independent columns. Okay. Now, let's rewrite that set of equations. So we want to solve this, right? We want to solve this. Instead, we solve this which is forced to have a solution. These are called the normal equations, or just the normal equation. You might see why the word normal is used here. But we still have one thing to know, right? Or one thing to figure out. But is the x hat that solves the normal equations guaranteed to minimize this quantity ax minus, or the length of ax minus b? So that's the thing that we have to check. Okay. All right. So note some facts. X hat is perpendicular. By construction, x hat is perpendicular, or I should say, maybe not x hat, but x hat is such that ax hat minus b is perpendicular to the column space of A. So it's perpendicular to every vector in the column space. Okay. Thus, so for any x, since ax is in the column space of A, and ax hat is also in the column space of A, this implies that ax minus ax hat is in the column space of A. Column space of A is closed under vector addition, so this is true. Okay. But then what this means, since this is in the column space, it means that ax, sorry, I wrote ax bar here instead of ax hat. So this is ax hat minus b is perpendicular to the vector ax minus ax hat. Okay. And so now I'm going to write some of these things. I'm going to write note ax hat minus b plus ax minus ax hat is the ax hats cancel. and this is ax minus b. But these two are perpendicular, right? So we have this sum. Since these two are perpendicular, what I know is that by the Pythagorean theorem, squaring these things, I have the sum of squares this is a positive thing I am adding to this expression, and it is equal to this other thing. So this implies that ax hat minus b squared, the length of this thing squared, is less than or equal to the length ax minus b all squared. Increasing function here. So this is what I get. So indeed, this is in fact exactly what I'm looking for. It minimizes this expression, right? This x is completely arbitrary here. We didn't do anything special with x. And this x hat that we found in this way minimizes this expression. It doesn't matter how many of them there are, even if there's infinitely many, all of them satisfy the same thing. They are exactly as close to this as possible. And so that is the deal. So solving the normal equations here is key. So that is exactly what it is I'm going to do. And so the process, we have ax equals b. Now you might say, what if I have an equation like this and it actually has a solution? Well, if it has a solution, then that solution will be the least square solution. And all this process doesn't matter because the thing you started with is already in the column space. Okay, so that projection essentially does nothing. It projects onto itself. It is itself. And in the event that, and this comes from the orthogonal projection itself, actually. So the orthogonal projection, the way it works is that in the event that the thing that you're projecting actually lives in the subspace you're projecting onto, in that case, it's simply equal to itself. So in that way, the least square solution is there's nothing to be done. It is just the solution you found, or one of the solutions you found. But if you are in the case that this has no solution, we solve A transpose A x equals A transpose B for a solution x hat that simply is our least square solution. Okay. These are my normal equations. So this is called a least square solution. To this equation star. Now, I think this is a good place to stop for today, since I only have a few minutes here left. This is a good place to stop and do a bunch of examples tomorrow and show what this allows us to do. So the main application that we are going to be able to apply this to is curve fitting. So what is this? Like I said, before we've done a single least squares problem here, I think it makes sense to actually see what it is. What's the idea here? The idea is, say that you have data points that look like this. Okay. Now the thing is that the way that these points are, you might have an idea or some intuition about what sort of shape these points fit. Now maybe you say they fit a line. Now what does it mean to fit? Well, I'm looking for, say, a line that passes through these points in such a way, and saying passing through these points is even a little weird because maybe it doesn't hit a single one of them, but it's like a line that is somehow simultaneously closest to all of these points while still being a line. So maybe it looks like that, right? And you would say, well, I have now fitted these data points to this line to try to indicate some some relationship between those things. Now you might look at this and say, well, I mean, do they fit a line, or is that just in my imagination? Have I tried to impose order where it did not actually exist? Because maybe someone else comes up to you and says, well, the line, that's not what I see. When I look at this, I see a curve that looks kind of like this. Right? And I feel that is more indicative of what's going on. But maybe someone else comes to you and says, actually, I see a curve that looks more like this. Right? So I I see I see some polynomial curve that looks more like that. That's what I see when I look at this. And you can see that in this case we have fitted those points to some other type of curve instead of a line or parabola or some other lower polynomial thing. Now, in the first two examples, you'll note that neither of them even actually pass through any of those lines. So, in the sense of seeking a closest solution, you can see where least squares may come in somewhere here, because all the points in question don't actually lie on the curves we are fitting them to always, but we are trying to get them like as close as possible, right? So in the case of the line, here are the distances we're trying to minimize, and we have a list of distances we're trying to like minimize simultaneously, right? That's kind of the constraints we're working under, right? And so when we talk about curve fitting, this is the kind of problem that we're having to deal with, where we are trying to make the best with these. The data points we have might be crazy, they might be all over the place, and fitting them so nicely to some high degree polynomial is just likely not going to be a thing that I can do. I'm going to have to settle for something lower ordered than this, either a line or a parabola, or like something maybe simpler. But the idea here is, in any case, questions about fitting data points to some curve that you suspect may be proper for modeling what's going on is going to involve these kind of errors, these distances that you are going to try to minimize, right, simultaneously. So anyway, that is where we're headed with all of this, but I think I have talked enough for today, and we're out of time. So that will be all for today, and I will see you all tomorrow.